Okay, moving along, our next speaker is Abigail Lee from Queen's University. Welcome.
Good morning, my name is Abigail, and I'll be presenting my research on star tracker algorithm improvements to restore performance after radiation exposure. I conducted this research during my undergrad at Queen's University through Sinclair Interplanetary by Rocket Lab. Star trackers are an incredibly important part of attitude determination. However, the longer they're on orbit, the more radiation they're exposed to, and the more their sensor degrades. Here we can see the effects of radiation on sensor degradation. The left image is a non-irradiated detector where a dark image has been taken. Since no light is hitting the detector, the background is quite uniform, and there are very few pixels at the high end of the pixel value spectrum. However, after using the same image with an irradiated detector to 13 kilorads, the background becomes much less uniform, and the mean pixel value has become elevated, making stars harder to see. The implications of this are that after enough radiation exposure, the star tracker will be unable to determine a solution due to an inability to detect stars or timeouts during processing. However, with key changes to the processing chain, Rocket Lab can restore performance after radiation exposure, allowing their star trackers to be used for longer missions or in harsher orbital environments. Looking at the processing chain, the first bottleneck identified due to radiation was in the sensor calibration. After the command is sent to take an image, the sensor must be calibrated to ensure that it has a sufficient signal-to-noise ratio and a sufficient dynamic range. Here's an example of an uncalibrated sensor. That star in the bottom right is quite hard to detect. The current sensor calibration uses analog offsets to set each of the 4 channels such that it has a sufficient signal-to-noise ratio and a sufficient dynamic range that is relatively equal across the sensor. This means after calibration, the background becomes much more uniform and the star easier to detect. However, the analog offsets are optimized at room temperature and not changed throughout the lifetime of the star tracker. This means this current sensor calibration cannot account for noise due to temperature or radiation. Calling back those images from earlier, we can see the limitations of the current sensor calibration. The non-irradiated image has a low mean pixel value, meaning a high dynamic range. After radiation exposure, that mean pixel value becomes elevated, reducing the dynamic range and making stars harder to detect. The second bottleneck identified due to radiation was in the lit pixel algorithm. The current lit pixel algorithm steps row-wise through the image, has a large window that is centered around the pixel of interest. The pixel of interest must be 70 counts or more above this large window average to be considered lit. In this case, this pixel will be lit, and the process is repeated for all pixels in the image. Processing this entire image using this algorithm, we get the image on the right. The current algorithm does a great job at identifying stars. However, it falsely identifies hot pixels as lit, thinking that they're part of the star. For every pixel determined as lit, the processing time increases, and we want to reduce that processing time. The effects of radiation on this process are that after radiation exposure, this image of Orion's belt, many more pixels are identified as lit, increasing processing time greatly. If enough pixels are identified as lit, then the star tracker will actually time out during its processing in order to maintain its update frequency. So after a certain amount of lit pixels, no solution will be found. To summarize, there are 2 key issues identified due to radiation in the star tracker processing. The first is the loss of dynamic range caused by the elevated mean pixel values that aren't being calibrated out. The second is the increase in false positives, causing the increasing in processing time. Thermal chamber testing was conducted in order to really quantify the effects of temperature and radiation on the issues analyzed. 5 irradiated detectors and 6 non-irradiated detectors were placed through thermal chamber testing, where dark images were taken from 20 to 70 degrees Celsius. Dark images were used in order to isolate for the noise due to temperature and radiation. Thermal chamber testing is also beneficial because any effects due to increased temperature can be used as a proxy for increased radiation exposure due to the similarities in their noise. Looking at the sensor calibration, this is a graphical representation of the images I showed you earlier, of mean pixel value across the detector. The solid blue line indicates the non-irradiated boards, and mean pixel value increases very little, resulting in only an 8.5% decrease in dynamic range. However, the dashed blue line, indicating the irradiated detectors, increases much more steeply and results in a 93% decrease in dynamic range by 73 degrees Celsius. To combat this, an alternative form of sensor calibration provided by the manufacturer of the sensor was analyzed. When on-chip calibration is implemented, the irradiated boards follow a mean pixel value that is much more similar to that of the non-irradiated boards, up until 53 degrees Celsius. Past 53 degrees Celsius, it still offers a 33% restoration in dynamic range. Again, calling back these images, we saw that that irradiated image had an elevated mean pixel value when using the current calibration. But when on-chip calibration is used, much of that dynamic range is restored. Thermal chamber testing was also used to quantify the effect of temperature and radiation on lit pixel counts. The dark images were processed using the current lit pixel algorithm. Because dark images were used, any pixel recorded as lit was a false positive and increased processing time. The red line on the graph indicates the number of false positives that can be detected in order to maintain the update frequency of the star tracker. Past this, no solutions will be found. The yellow line representing the non-irradiated boards does increase in false positive count with temperature. However, it never exceeds this lit pixel limit. Whereas the purple line representing the irradiated boards exceeds this limit at only 35 degrees Celsius. Now, when we implemented the on-chip calibration, we were able to reduce lit pixel count and sustain performance to 47 degrees Celsius. However, further performance enhancements were desired and sought out through changing the current lit pixel algorithm. So the first proposed algorithm was the neighboring pixel algorithm. It still steps row-wise through the image and still has that first conditional that the pixel of interest must be elevated above the large window. However, it carries a second condition that the pixel directly to the right must also be considered lit and 70 counts above the large window average for the first pixel to be lit. Processing this entire image using this algorithm, we get the image on the right. So the neighboring pixel algorithm does a better job at classifying hot pixels as part of the background. However, because of that second condition, it will always clip the right side of stars, resulting in false negatives. This will likely impact the star tracker's ability to determine a solution. The second algorithm proposed is the small window algorithm, again, row-wise through the image and has that same first condition. However, this one carries the second condition that the average of a small window centered around the pixel of interest must be 50 counts or more above the large window average for the first pixel to be considered as lit. This is because this algorithm is looking for sections of elevated pixels that would indicate a star is present. Processing this entire image using the algorithm, we get the image on the right. The small window algorithm does a great job at identifying stars and properly identifies hot pixels as part of the background. Processing the thermal chamber images using the neighboring pixel algorithm, false positives were able to be reduced and allowing the star tracker to perform up until 67 degrees Celsius. Processing using the small window algorithm, we saw a similar performance in the false positive count, allowing the star tracker to perform to 65 degrees Celsius. So looking at this graph, implementing just the improved algorithms, we were able to see a sustained performance increase of 20 degrees Celsius. But implementing both the improved sensor calibration and those proposed algorithms, we were able to see performance increase of 30 degrees Celsius. Now, while these results were promising, it was important to see as to whether the proposed algorithms affected the star tracker's ability to detect stars, as you gotta remember that these were dark images being taken. So to analyze this, simulated star field testing was conducted using a star tracker optical simulator. Dynamic images were taken and processed using the neighboring pixel algorithm, with the large window threshold being varied. The large window threshold was varied in order to determine its effect on the algorithm's ability to detect stars. The blue line indicates that past a threshold of 57, the true number of stars in the scene will never be detected as the algorithm is being too restrictive. Thus, in order to maintain the performance of the star tracker, a threshold of 57 or below must be used. The same process was performed using the small window algorithm, but since two thresholds were present, both were varied. For a small window threshold of 60 or greater, we will never result in the true number of stars being seen. Thus, small window thresholds of 40 and 50 must be used, with large window thresholds of 70 or 60 and below. In conclusion, using thermal chamber testing, I was able to see a performance increase of 30 degrees Celsius when implementing the proposed algorithm and improved sensor calibration. Using temperature as a proxy and ensuring algorithms are optimized for star detection, results showed that the improvements could increase the radiation tolerance of Rocket Lab star trackers, allowing them to be used for longer mission lifetimes or in harsher orbital environments. There are some key next steps in this research, though. The first is on-orbit testing that is currently being pursued. This is important to analyze the effects of the proposed changes in an orbital environment, as so far it's only been simulated. The second is once the orbital testing has been done, it's important to quantify our new mission lifetimes and temperature ranges for these products. Using both the orbital testing and the total ionizing dose investigation, an algorithm will be chosen and implemented into production. I'd like to thank my advisor, Brent Breakbore, and all of the support that I got from the Rocket Lab team throughout this research. I'll now be taking questions.
Okay, judges? Go ahead, Jay.
So what method did you use to create the irradiated boards, and how confident are you that that method will match the actual in-space characteristics?
Absolutely, that's a really great question. So we use a lab located in British Columbia, up in Canada, which uses the boards and places them near a radiation source. And then they, from there, and the data that they collect in their lab, give us a rating of how much radiation our boards have been exposed to. And while I can't be necessarily confident that these are going to be exactly the same at some of the satellites that are going to be on orbit, because that radiation will vary, we're able to use this to see if this method is even worth pursuing on-orbit testing. So that was the goal of this research.
Others?
So you mentioned the next step is on-orbit testing. Are there risks that you know that that would buy down by doing on-orbit testing specifically, or just on-orbit is better than in a lab?
So, great question. We've noticed, at least using our Star Tracker optical simulator, it's easy to overfit to an algorithm. And so that's something that we want to avoid. And we want to take the improvements that we have and really fit them in an orbital environment. In terms of risks, the on-orbit testing that we're pursuing is using a decommissioned satellite that still has an active Star Tracker. So any risks imposed by us uplinking our firmware are very minimal.
Okay. Anyone else? If not, I've got one. But I'm going to give the judges first right. Go ahead, John.
Kind of a follow-on question about the irradiated boards. Like in space, is it are the star trackers? Is it usually a permanent damage to it, or is it more of a temporal that they can kind of pixels can kind of come and go and be problematic? And is that relevant? I guess is the question.
Yeah, absolutely. So after radiation exposure, sometimes we can go through the process of annealing, so exposing the board to a temperature to kind of reduce those effects of radiation. However, because of the kind of build of the Star Tracker, it's not quite as easy to anneal the Star Trackers on orbit. So while customers could place, temperature heat sinks on the lenses quite easily, kind of inside on that board would be quite difficult. So it would be hard to get the restorative effects of annealing for the radiation exposure. So it is most of the time, damaging permanently.
Okay, thank you very much.
Awesome.